So today we are going to stop at just about the perfect part. We're going to spend a little short section here, giving some more properties of symmetric and alternating groups. And then we're going to go into group actions, and we'll see the symmetric groups coming up. And group actions as well. So let me remind you that I'll just call this definition. Let's let A be a set, not empty. And SA is the set of F from A to A, such that F is by A. So what I'm calling S sub A is just a set of all functions that go from the set to itself, and the function has to be one-to-one and onto. If A set of numbers 1 to up to N, we write Sn or SA. So if this set of the finite, and so we've seen this. This is a group. A group under function composition. And it is called the symmetric. So it's just called the symmetric. And Sn is one that's quite common because oftentimes the one on the finite sets are used quite a bit computationally. So let me give you kind of a quick example here. And this has got some foreshadowing to it, I think. Actually, I'm going to do something here. Let's look at the dihedral group. You're used to me putting the vertex up here, but I'm going to actually put the flat sides here. If I rotate this, whatever it is, 60 degrees clockwise, then 1 goes to 2, 2 goes to 3, 3 goes to, and 6 goes to 1. Everybody agree with that? What happens if I flip this about the y-axis? Rotate about the y-axis. Where will I get now? 1 and 6 swap, 2 and 5 swap, and 3 and 4 swap. Notice also automatically I get this. Let's just see what I get just for fun. Usually I start these permutations at 1, but I'm going to start at 6 here. It doesn't matter just because I know what's going to happen. It's be interesting. Where did 6 go? Good. It goes to 5, doesn't it? 6 goes to 1, then to 2, then to 5. 5 goes to 4. 4 goes to 3 goes to 2. So if I rotate flip, what happens? I rotate it backwards. So this is our inverse. So what happens if I take the rotation in this flip and I generate this? It makes a little dihedral group on the hexagon. Agreed? D6 has what? 12 elements, right? How many elements does S6 have? Symmetric group on 6 letters. It's got 6 factorial, a lot, right? 720. So this actually makes a little subgroup using this cycle and this this little element of order 2, right? And that makes a little subgroup inside of there, right? Inside of it. And we're actually going to see how we're going to get a theorem later that shows that if I walk up to you in any group, you can realize that group is a subgroup of some symmetric group, right? Just like we put the dihedral on 6 inside of that 6. I can do that with any group. I can put it inside some symmetric group. By the way, just for fun, turn this thing 30 degrees so that the top vertex is here. So you do the other flip and you will get basically the same subgroup as you should. Okay. You follow definition here. Definition. Let sigma of A1, A2, and here, M, so let's say we're equal to N, and AI AJ with I. So what I'm saying is I've got a single one of these cycles, and these are all different, right? So for example, 1, 2, 3, 4, 5, 6, but I'm just saying all of these are different here. This is called an M cycle. If M equals 2, sigma is called a transposition. So a transposition is just what I get when I swap just 2 things. An M cycle swaps one single cycle, things like this. So for example, 2, 1, 4, 3, 6, 5, 7 is a 7 cycle. 1, 4 is a transposition. 1, 4, 2, 3, 5, 6 is neither. This is a product of 3 transpositions, but it's not a transposition itself. So here's a fact that should be fairly easily. What's the order of an M cycle?
Well, in, or
Right. That's how many times you gotta do it to itself before you get the item. Also, if sigma 1, sigma 2, this is factor peg class, are disjoint cycles of weight M1, M2, MT respectively, then the order is the least common multiple. And this is actually something that we've seen earlier, homework. Yes, it's going. That means that there's no number in this one that's in this one. All right. Right, so this right here is disjoint transpositions. Not, because they share a one. Same. So here's the theorem, which I'm going to go for the details of, but I'll kind of talk to in a moment, or well, I'll wave my hands a little bit. Let sigma be known as m, then sigma can be written as number one, a product of disjoint cycles. And when I write something in SN as a product of disjoint cycles, there's only one way to do it, up to permuting the cycles. Two, a product of transposition. Not necessarily, or not uniquely. Like never uniquely, really. Okay. The product of disjoint cycles. So if I take an arbitrary notice this algorithm that I taught you basically tells you how to write the function. Basically, this is a function that goes from 1, 2, 3, 4, 5 to itself. And so what we're doing here is we start with 1, it goes to 3, 2, 4 to 3. 3 goes to 1 to 3 to 1, 2 to 4. 4 goes 1 to 3 to 5. 5 goes to 2, 4, 5, 1. Where does 2 have to go?
itself.
It has to go to itself. It's always good to check all gems, so let's do that. 2 goes to 5, 2, 1 to 2. Good. Notice what this algorithm does is it closes the cycle, right? So they get some of the elements, and then you start over again, and you keep closing the cycles off, and that's why you can basically write everything as product of disjoint cycles. Right? So take it easy. So take any element of your domain and you follow it till it cycles off. And since the map's bijection, just pick it up with the next thing. This algorithm will always terminate. Yes.
We still consider that an M cycle because of the fact that the other one is just a one cycle.
Yes, you could write this as a 4 cycle, right? Because this doesn't count in certain, right? That's a good question. Now, well, probably, I'll demonstrate this a couple of ways. Notice A1, A2, AN, yeah. Is one cycle. Anybody see how we can write this as part of transpositions?
A1, A2, A1, A3. The, yeah. It's,
Let's see what happens. Where does A1 go? It goes to A2 and then there's no more. Where does A2 go? It goes to A1, now to A3, and there's no A, right? Where does A3 go? It goes to A1 and then the next one gets to A4, and so forth and so on. And finally, where does AM go? No AMs, it goes to A1. So I can write that M cycle as a product of transpositions that all have an A1 in them. Notice they're not disjoint, right? And so if I can write something as part of disjoint cycles, just take every cycle and break it up like that, and now you get this one. Yes.
You said number uniquely, so can I start with any, like instead of A1, start with AM?
Well, what I mean by this is, here's the problem. That's about the easiest thing that I can think of that I can write, right? This is equal to. And it's also equal to. Shoot, even the identity. Right? These two collapse the identity, and these two collapse, these collapse, these collapse. So I notice how, what an obnoxious thing that is. I've written the identity as a product of 8 transpositions, right? And that's what I mean by never unique, because if you write something, you can always stick on, whatever you write down, you could always stick on a pair of transpositions at the end, and that's right.
But you started A2 for that though, quickly,
Yes,
okay.
absolutely, right. Yeah, because this cycle is the same thing, it's A2,
Okay.
A3, AM, A1. And then you just do that one. Okay. Definition.
I just wanted to remember, because we were talking about cycles quite a while ago. I just want to remember, so a cycle is technically, it's a function that's mapping each of those thing next to it.
Right, it's not as general as permutation, but a cycle just kind of cycles back. One goes wherever it goes, and that goes somewhere, and that goes somewhere, and you eventually come back to one. That just doesn't cycle.
Yeah, because I remember like that, how to do the, whatever, calculate. But I didn't remember exactly what their functions were.
Okay, definition. So this is far as follows. Let sigma be any permutation in S. We say sigma is even if sigma is and even, uh, let me, sigma can be written as a product of an even number of transformations. Sigma is odd if sigma can be written as an odd number of transformations.
Are they mutually exclusive?
You preempted me. That was actually the question I was gonna ask. The first thing you should do is be critical of my definition. When I write it up there, how do you know that this definition is well defined in the first place? Right? How do you know that deep in the depths of some Stephen King novel, there's some element of SN out there that you can write this way is a even product of transpositions, and over here is some odd number of transpositions. Can such thing be done? I mean, if it can, I probably should have really made this definition, right? Because if you can't sort them out that way, now look, here's a great example of the identity. The identity can be written in zero transpositions, right, which is even, but also A. I notice here that this one, by my definition, should be odd, and when I wrote it these other ways, it seems to be odd as well. It seems to hold water, but we should actually prove this. And actually, we were going to do it.
Yeah, I've heard this formally. I'm trying to think, there's counter example there.
Sometimes you do
That's
have
essentially the way it's gonna work. I mean, what we're going to do, the strategy is. We are going to try to. We are going to assume that there is out there some permutation that is both even and odd. And we're going to try to isolate the smallest one, get confidential. So let me give you a theorem. No, no sigma in SE, both even and odd. So definition 445 makes sense. So it's well defined. When I say something's even, it's always, when I say something is odd, it's always odd. Let's prove this. Let me give you a setup first. Let's suppose that the theorem is false. That is, suppose we can find sigma SN such that sigma is even and odd. Okay, so what does that mean? That means so it means I can write sigma two ways. So I can write sigma equals tau one, tau two, up to tau two n. And some other Greek letter, 101, 182, 1. Where tau, pi, tornado J are transpositions. Right. Okay. Let me ask y'all a question. What is the inverse of transposition?
In tornado, what letter is that? Is that the C or something?
See, something like
L,
that,
what's it for?
slash XI.
Oh, okay.
That's what it is in LaTeX, so.
Okay. I think that was C, but.
So, what's that?
What's the, it's not itself?
That is correct. Any transposition is its own L inverse, right? Because when you swap A and B, its inverse is to swap them back. Everybody agree with that? So I can massage this a little bit, and I will. I want to hit both sides of this on the left with tau 1, then tau 2, and so forth. So the tau here. 1, tau 2, 1. It shouldn't. Everybody see what I did there? I successfully hit tau 1 on the left and tau 2 and tau 3. And so I sort of broke this thing up here, canceling this term by term. Right, all right. And I'm gonna, so what does this mean? Notice that, how many transpositions do I have here? I've got 2n plus 2m plus 1 transpositions. This is odd. So the identity can be written as a product of odd number trans. Everybody okay with that? So if there is a permutation out there that's both even and odd, from this it follows the identity can be written as an odd number of transpositions. Everybody agree? So we assume. So I'm gonna, instead of, this is getting out of hand here with all the 2 N's and 2 M's and such, so I'm gonna collapse this. So we can write the identity as alpha 1, alpha 2, alpha k, alpha 2k plus, where alpha I is. So that's where we are so far. We've deduced that out there, if there's some permutations, both even and odd, then I can write the identity as a product of an odd number of transformations. Everybody agree with that? What's the smallest positive odd number that you want, or that you can think of? One. It's clear, is it not, that the identity cannot be written as a single transposition? Right? Because by definition, you're swapping two things. That can't be the identity, right? But even at 3, it starts to get a little bit mysterious, right? Perhaps. And by the time I get to like 17, it's like, how do you know that there's not some kind of way that you can juggle it around? Well, we've got to show, if I show that this is poppycock, this can't happen, then I'm done. Everybody agree with that? Because then the identity can't be an odd number of transpositions, so that could have never existed. Everybody agree with that? Now, here's where I'm going to do some computation. I'm going to develop some rules, and what I'm going to do is I'm going to take this transposition here, and I'm going to move it all the way to the other side, from right to left. Now I'm going to show you how to do that, and these are all rules that we know and we compute ourselves, and we'll do some. So I am going to make some rules. For moving a transposition. From right to left. And the idea is I'm gonna take this transposition here and I'm gonna move it to the other side of all these and see what happens. Let me point out that one, AB, AB, what happens? What's the product of those two transpositions? This is the acronym. Right? Now I'm gonna do ACAB. So what this says is, if I'm moving from right to left, if this transposition ever encounters itself right next to it, they cancel, right? What happens if AB encounters AC? So they've got one thing in common, not two, right? Well, this is, A goes to B, C goes to, A, or B goes to C and C goes to A. And this can actually be written as AB, let me check that. A goes to, oh, no, I guess it's BC, isn't it? Typo then? That should be right. If we look at this now, A goes to B, correct. B goes to C, correct, and C goes to A. So if AB encounters an AC, then you can lop it out doing this rule. It moves to the right, leaving BC in its wake. Right? What if we have an encounter like this? AB, BC. Yeah, BC, AB. This in principle is similar because they have the same, they have something in common now, it's just B instead. This is A, C, B. And this is ACBC. If I agree with that. So now what happens if AB encounters, and it's similar in the other one, then now it comes through as AC. So it changed it a little bit. All right. But notice BC, there's no A. That's the point. Notice AB, no A. When AB hits AC on this side, you move through and there's no A. When AB hits BC on the side, you move through, change it a little bit. There's an A here and no A here, right? And the last one's the easiest one, sort of. What happens here? Here, I didn't say this explicitly, but I should now. I'm assuming that A, B, and C and D are all different. Now you can just move with impunity because these are disjunct cycles that you get. So this is A, B, C, D. Now let's alpha to alpha to one step by step to left side. Transition. So this is what I'm saying. I'm gonna take these two and swap them. Applying whichever rule I need, right? And once I've swapped it here, then I'm gonna swap it here, and I'm gonna keep doing this. I guess I gotta do it 2K times until I get all the way down here. I agree with it. So I keep swapping them, and every time I will apply this rule. Now let's think what has to happen here. Suppose we never use suppose that in doing this, so I keep swapping this out and moving it all the way to the left. Suppose I never use this rule. Okay, suppose that never happens. Agree? What does that mean? That means when I do the swapping, I get E equals alpha 2K plus 1 prime, alpha 1 prime, alpha 2 prime, alpha 2K prime. And I put these primes here because doing the swapping might have changed the original things here, right? But if I never use rule 1, what must be true about alpha prime 2K plus 1? If I never use rule number 1, then it has to have an A in it. Everybody agree with that? Because every time I use this rule, your A survives. Your A survives. Your A survives. So this has to be a X. I don't know what X is, but some other X that is changed into, correct? And A is not in any alpha T. Because notice, not only does A survive, A survives, A survives, A survives, but there is no A in the wake, right? A is destroyed, A is destroyed, A is destroyed. Agreed? Anybody tell me what the problem is? So here's what this looks like. If you wrote it out. This becomes AX, and then some other stuff. Let's say D1, two up to E. Okay, -1 E. Okay. None of these DIs be A, correct? So what does that mean? That means this permutation takes A and X, where X is not equal to A. Right? Because look at what this, I don't care what happens to the others. I don't care what happens to the others. Look at what this permutation does to A. No A, no A, no A, A goes to X. It can't be the identity. Everybody agree with that? Can't be the identity because going through this process here, whitewash all the A's out except right here. Right? A has to go somewhere and it has to go to X. It's not A. It can't be the identity. Everybody okay with that? And what about contradicting? What's in there?
Okay.
Now, what's the assumption that I used to get, when I went all through all this rigmarole, I got the AX. What was the assumption I made?
Don't use rule one.
I never used rule one, so it must be the case. One that says AD, AD, C. But see what the problem with that is? What happens then?
Well, you can just rewrite it as that, so minus this. Very good.
But when we apply this rule, the two transpositions cancel. And we now can write E as a permutation or as a product of two K plus one minus two.
And then you just repeat the process until you get to one term, which isn't B.
Right. Equivalently, you contradicts the minimality, right? Because we have this odd length, product of transpositions that was of minimal length. Now I've shown that I can write one, and he brings up the point very well too, that you
Where
can
did
just,
you say that it was minimal?
maybe I forgot to say that.
Or
I
I
had
to
to
describe like version, like repeating terms like mathematics.
Right, so I may have forgotten to say that, but I wanted to say that my odd transposition was evenly, remember how it clearly can't be one.
Right.
Right, and then after that, it got fuzzy, well, you can assume it's odd of minimal length,
Okay.
but even if I forgot to say that, which I probably did. And now what you can do is you can write it small, as a small length, now start the problem over again, and you can do it again and again until you get down to one, which is an obvious computation. Okay, any questions on that? Okay, so we've got a big theorem now, and that is important because now we know that an odd is an odd and an even is an even. Let me ask you this. What happens if I take, now that I know this is well defined, what happens if I take two even permutations and I multiply them together? What do I get? It's still even, isn't it? What happens if I take an odd permutation times an even permutation? It should be odd, right? Because you're adding up the transposition. What happens if I multiply two odd transpositions? What do I get? An even, right? This allows us to do the following, and this is kind of a words. Definite. Or 7. Be defined. A n be sigma and S n, so it's the sigma. This is called the alternating component. No. A. So. How should we prove this? Yeah, it is. You could do that, but I got a slick way to do this. Theorem. I'm gonna make it strong, say. 4, 4, 8. All n greater than or equal to 8 n is a normal subgroup of SN. By the way, what's the order of AN? How many elements do you think you have? Correct. Basically, in SN, half the permutations are even and half are odd. Now, some of this may be a little bit unclear. I mean, I haven't even said that A is a subgroup, and all of a sudden I'm saying it's a normal subgroup. Let me give you a proof of this.
We only really have like 5 minutes left.
Huh?
Like 8:46.
You underestimate, so.
That is, yeah, I mean, you know, we like challenges here.
Define the following homomorphism from SN to C2. B sigma is equal to 0 if sigma and 1 bar of sigma is odd. Okay. Notice that phi of sigma 1 sigma 2 is equal to phi sigma 1 plus phi sigma 2. I'll let you verify this. It's a homomorphism because it's pretty. I mean, we've just essentially been through it because what happens when you multiply two evens? You get an even. That translates to 0 plus 0 is 0. What happens if you have an even and an odd?
On.
It's
Or
odd,
even-
and
wait.
that's 0 bar plus 1 bar is 1 bar. What happens if you have two odds?
Even.
You need 1 bar plus 1 bar is 0. Everybody okay with this being a homomorphism?
Yeah, it's already being a homomorphism.
So
Oh, now I see. I want to use the homomorphism rules, make sure that's, you know, normal homomorphism.
what's the kernel of this map?
Well,
It's everything
AN.
goes to 0 bar. So
it's AN.
that's right, this is sigma such that sigma even, which is exactly equal to AN. So immediately, AN is normal in SN because it is a subgroup, because it's the kernel, and it's normal. Bang, you're done. Everybody okay with that? And the index of AN and SN is exactly equal to 2 by first isomorphism. And Lagrange. Because SN mod AN is isomorphic to Z2 because this map is on 2 because N is greater than 2. That means there's 2 left cosets of AN and SN. So that means that since the index of AN and SN is 2, this implies that AN is exactly half of the symmetric. Okay. And for the record, I did it in 4 minutes.
Well,
Any questions?
that was pretty good.
All right. Y'all have a good one. We'll start on group practice next time.
Yeah, I'll probably just head over to your office and then do like, that's what I need to do with how to improve, you know? Trying to improve if I can improve some stuff.